Let's look a little more carefully at two of our assumptions from the last panel. First of all, about the base current that we would compute here. So we're trying to compute this current. Here's the problem with what we did before, which is that I said that when I put this wiper up to the point where there was 5 volts on the wiper, that I was going to figure that that whole 5 volts was across that 100K resistor. And that's not true because, in fact, there is a voltage from the base to the emitter. It's not just a free connection between those two. And here's how to think about that in general. The base to emitter junction is as if it were a regular silicon diode. So I sometimes draw that in here, right like this. And you remember that a silicon diode has a forward voltage of 0.6 volts, roughly. So in fact, the voltage at this point is 0.6, not 0. And the voltage across the 100 kilo ohm resistor in this instance, if this wiper is up at 5 volts, is 5 volts minus 0.6. And so the base current is not the full, now it's 50 microamps, 5 volts divided by 100 kilo ohms. It's not the full 50 microamps, but rather 5 volts minus 0.6 volts divided by 100K. So the base current is only 44 microamps. Not that big a difference at this point, but as you slide that wiper down, you might expect that the base current goes smoothly down to 0. It's going to go down to 0, but it's going to go down to 0 at the point where this becomes about 0.6 volts, well before the wiper of the potentiometer reaches the very bottom of its range. Okay, so that's one assumption that we've done a little bit more accurately now, that the base to emitter voltage is as if it were a diode, and the voltage from one to the other is about 0.6 when it is conducting. And if you put a voltage here less than 0.6, nothing happens at all. No current flows into the base at all. The other thing that we should clarify is what happens if we start to get large collector currents. So let's take it in this instance. Suppose that the base current is 50 microamps and the gain is 100. The current gain, HFE, is 100. So that means that if the base current is 50 microamps, the collector current, this would predict, would be 5 milliamps. Well, that's starting to be a little problematic because 5 milliamps times 1,000 ohms is 5 volts. That says that there's 5 milliamps flowing here, 5 volts across that 1 kilo ohm resistor. You'd see that this voltage now must be 0, and that might make you suspicious. What if I had increased this base current a little bit higher, and the base current were, say, 100 microamps? Well, 100 times that would be 10 milliamps, and that would say there'd be 10 volts across. Now, that can't be. Something must be wrong here, and indeed there is. You couldn't possibly get 10 volts across that resistor. Where would the 10 volts even come from? And that would predict that the collector, the voltage at this point with respect to ground, would be -5. That's crazy. So what's gone wrong here is that no matter how much base current you put through here, you can never reduce the collector voltage below that of the emitter, below 0 in this case. That value, in fact, you can't even get it quite as low as 0. The lowest voltage from collector to emitter, VCE that's called, is the saturation voltage. It's abbreviated in your data sheet VCE sat, and it's typically quite small. It might be as small as 0.05 volts, but it's certainly not 0, and it's certainly not negative. So you can never, no matter how much base current you put through here, you can never get more collector current than would be required to reduce this voltage from the collector to the emitter down to 0. When you've done that, when you've reduced the voltage across the transistor from collector to emitter to as low a value as it can go, or to 0, we call that situation saturation. That's as conductive as the transistor can get.